So let me begin by saying what is the problem. So first I want to set up some notation because we may be from different fields and my notation may be different from what you're used to. So I define Hn to be the Boolean hypercube and x is uniform on the hypercube and y is obtained by flipping each bit of x independently with probability 1 minus rho over 2. So just to get the feeling, when rho is close to 1, you don't flip, so you essentially y is approximately x, and when rho is close to 0, y is independent of x. This is just the notation. And we also define a noise operator. So you're given a function that maps the hypercube to real numbers. We define T rho of f as the conditional expectation of f of y condition x. Also, I will use the following notation for the binary entropy function, which is this is the standard binary entropy function. And another notion which I'm familiar with in my main research area, but you may not know, is the notion of mutual information, where we define mutual information between ix, y is a function just of joint distribution with the expectation log likelihood between the joint distribution and the product distribution. So these are the notations. If anybody has questions, you can ask me now. Otherwise, I hope it's kind of standard. Yeah.
There's no n there in the binary.
Oh yeah, sorry. The slides were made last night, so I apologize. Thank you for pointing out it's important. Yes. Okay, so the story goes back to 2012 when Gautam, who is pictured here, he asked me the following question long back, that if you have a Boolean function that maps a hypercube to plus minus 1, then is it true that the mutual information between fx and y is maximized by dictator? So my first response to him was, I'm not in this area, but you should ask somebody in Boolean analysis and they should be able to answer this to you in 5 minutes. And I was completely wrong. This problem is still open. And so the question is, and then Tom, who's here, he became a postdoc at Stanford, and he and Gautam wrote a paper which gave a lot of evidence to why this may be true. And so the conjecture states that if you take any Boolean function that goes from hypercube to minus 1, then the function that maximizes, the Boolean function that maximizes the mutual information is the dictator function. It could be any I, but it's the dictator function. There's a lot of things known about this conjecture, and I'll probably get to some of the latest developments at the very end of the talk if time permits. But I want to tell you one of the things that's already proved by other researchers. So a few years later, actually 2016 or something, they proved, these researchers proved that instead of asking f of x with the whole of y, if I now ask what is the maximal mutual information between f of x and another Boolean function g of y, then it is shown that dictator maximizes it. So this much is known. So at least there's partial evidence in this form that it's probably true. So if you need to compress that to a g of y, then the best thing is infallibility dictator. Okay, but now I'm going to shift and go to a different conjecture. So a few years later, in a workshop in Simon's Institute, that's why we have many authors here. We were just talking about the mutual information conjecture, and basically Jairam, Amit, and myself, we decided, what if we replace the binary entropy function by 2 square root x into 1 minus x, because that's related to Hellinger. That's why I'm calling this the Hellinger conjecture. We will get the following conjecture. Is it true that this inequality is maximized by dictator function? Because dictator function achieves this. So instead of entropy, we are putting another function here. And I want part of this whole talk is to argue and suggest that this perhaps is the more interesting conjecture from a mathematical point of view. Both are interesting, and I will tell you why. So the first thing we showed is that if you prove this conjecture, it implies the mutual information conjecture, which means this is kind of a stronger version and the measurement conjecture. Of course, that's not shown yet, and so this is also not known yet. So another question you can ask is, what if I ask the same question, that if I restrict myself to pairs of Boolean functions, is it true that this object is maximized by the dictator function? You could still have the weaker form. To the weaker form, I have a partial answer, and I'll tell you why. So I believe the weaker form is true, and I hope in the next two slides you will agree that there's enough evidence to convey that the weaker form may be true. So the first statement I'm going to put a conjecture in with a dagger, because you will see later, is that let us take any two binary variables u and v, with v taking values in -1, 1. Then the conjecture is that the following inequality holds, where this is an inequality where S dagger is a quantity I'm going to define soon. It's related to the reverse hypercontractivity between u and v. So what do I mean by reverse hypercontractivity? I say that random variables u and v is said to be PQ reverse hypercontractive if the expectation is bigger than FU P prime and GVQ for any non-negative functions f and g. And for a fixed P, you define SP to be the maximum of Q minus 1 over P minus 1, and that's the SP. So you let P go to 0, and then you have this S dagger UV. So S dagger UV has a nice characterization in terms of Kullback-Leibler divergences. So that was the kind of motivation why I wanted to use this parameter, and you could do some simulation. You could see this perhaps is true. So now we have so that led to another conjecture. So you see it's a whole talk about conjectures. So for any three variables S, C, D taking values 0, 1, we believe that this 3-point inequality is true. So this we can do extend simulation. This is just there's nothing unknown here. We can just plug in numbers, ask the computer to check. This seems to be true. And you can also prove it near the equality points. So it's possible, given the computing power that we have, we can get a formal proof. But I didn't really bother with that. But I believe this is true. But if this is true, this will formally imply the previous conjecture, and hence the weak form of the Hellinger conjecture. So that's why I put a star there saying that this is just a three-point. It's an algebra question, and you can simulate it. It seems true. You can find enough evidence that this is true. And if this is true, the previous one is true, because what I'm doing here is that this is the formal upper bound to 1 minus S dagger. You can prove that this is the formal upper bound to 1 minus S dagger, and then you use this guess for the upper bound and show the inequality. So that's the very brief beginning to the two conjectures I stated. I still haven't, and I just want to mention this may also be of deep interest because it just concerns binary random variables. Okay. Any questions so far? So this is just some introduction. So now let me go to the second part of my talk. What is the link to isoperimetric inequalities? So when the flipping probability goes to 0, that means rho goes to 1, the Hellinger conjecture is equivalent to stating that the expected value of the square root of the sensitivity of the function f, which p at x, that the number of neighbors with the opposite sign is at least bigger than 1. That's the statement. Now, there is a result by Talagrand which says that if you take any set A in the Boolean hypercube and you define the function ha of x to be the number of neighbors which has a different sign than the value in A, if they're not in A, then he proved that the expected value of square root of ha is bigger than this function. Square root 2 times the measure of A times 1 minus measure of A. Now, so you can observe that the sensitivity of a function at a point x is just square root of hax plus square root of ha complement x. So it's just you add the the set and it's complementary. So Talagrand's result implies that when the set is balanced, that there are equal number of plus and minus ones, the expected value of square root of sensitivity function is at least square root 2 over 2. So you don't have 1 yet, but you have square root 2 over 2. Now Bobkov, around 96, he has a result which I'll go to later, but he showed that you can get to square root 2 over pi, which is a bigger number than square root 2 over 2. And then there's recent developments here. So instead of looking at a square root, if you look at ha to the power around 0.58, then Jeff Kahn and Jin Park showed that this quantity is bounded by 2 mu a in 1 minus mu a. So if you could replace this 0.58 by 0.5, then you would get the at least the limit rho tends to 1 version of the conjecture. And following this, if you just understand Jeff Kahn's and Jin Park's work, it's not hard to see that you can improve their estimate and get up to 0.53. So there's a recent work that shows that you can get until 0.53 you can get 2 mu a in 1 minus mu a, and they also showed that the expected value of square root of sensitivity at least 0.91. So that's the best known bound so far. So you're getting closer and closer to what we believe to be the right answer, but we're not yet there. And this is just as rho tends to 1.
Sorry, so there was a more recent paper. There was a presentation here a few months ago. Yeah, I think what's the exponent now? 0.500.
Just above 5. Okay. Good. Thanks. So it's almost. So not yet 0.5, but just above 1. Okay. So yes, but you will come back to this in the end, where I think that even this is just rho goes to 1, but even if rho goes to 1, we're not yet done, because okay, so this should be corrected to 0.5007. So you see that this is the area work, so that's what I'm aware of. And you can see that if you take f to be the majority function, you can show that whenever alpha is less than half, then you go below 1. So clearly that's the best you can ever hope for. So the visual conjecture we studied a lot in the infinite theory community, in particular there's a lot of related noise, non-interactive correlation distillation, whole bunch of work which I don't have time to go into. But one of the things I want to say is that it's known to be true when f is balanced and for low rho less than 0.44. This is a work by Liu published last year. And there are several versions of which we studied. So this is kind of there's some history here, and then the part 2 of the work, which is now I'm coming to, is that we want to go between half and 1 in some way for this family of conjectures. So we're going to define this is work with my student Chen Zije for the last 2 years. We define a new family of alpha divergences that interpolate between Hellinger, Jensen-Shannon, and chi-squared. And then we will show that the optimality dictator for these families is a nested family. So if we show it for one parameter, then it follows for all the parameters after that. And then we prove a new lower bound of Hellinger conjecture using isoperimetric. So this is part 2, and then at the end there will be a small part 3, which is ongoing work. So this is the first introduction. So really my work on this problem has been 3. The first is all the work till 2015, then this period of 2 years, and then after I was invited to the workshop, I said maybe I should think about it a bit more, and that's the last part of the work. So we define this kind of complicated looking function, phi alpha p is a parameter between 0 and 1, to be the following quantity. So it's 1 minus this binary entropy of p, when alpha is 1, its limit alpha goes to 1, you get this. So this is our definition of phi alpha p. And you can think of phi alpha p as a sort of divergence between the two-point difference p1 minus p and 1 minus pp. So we're going to list some properties of phi alpha here. When alpha is half, you get squared Hellinger distance. When alpha is 1, you get the Jensen-Shannon divergence, which is here. And when alpha is 2, you get Pearson chi-square distance. And phi alpha has a property that phi half is 0, it's decreasing convex, and so on. So it's a nice family of functions. And the main point is that, so we can define the phi alpha conjecture the same way. So think of, so for a given phi alpha, we can ask which Boolean function maximizes the phi alpha entropy. Phi alpha entropy, because phi is convex function, you can define the phi entropy. You can ask which function maximizes the phi entropy, and we believe that it's maximized by theta. That's what the statement says. That's the phi alpha conjecture, and this is for alpha between half and 2. So it was an attempt to get between, maybe to get a family so that we can at least get something from family. So the first result that we showed in this context is the fact that, first observation is that at alpha equal half, this corresponds to the Hillinger conjecture. Alpha equal to 1 corresponds to mutual information. And alpha equal to 2 is, you can prove this it's a very straightforward thing to prove that it's true. So this kind of interpolates between the three main, 3 points which are kind of interesting. And as a rho goes to 1, each of this becomes explicit value sensitivity of alpha, sensitivity of to power alpha bigger than or equal to 1. So now we know that it's true for alpha bigger than 0.507. So at least that part seems to be true. So the first theorem for this statement is that if phi alpha holds for any alpha in the range half to 2, then it also holds for any beta satisfying beta within alpha. So in particular, it's enough for you to prove it's some alpha, and the rest is automatic. Okay, so that's kind of the idea. So I'm just going to give a quick proof sketch, but it's not really. There is some calculus, but it's not very enlightening. So you can define psi alpha to be just 1 minus phi alpha, and the inverse mapping was increasing. Then you can show that psi beta, psi alpha inverse is non-negative increasing, but the hard part is to prove that this function is convex in Y. So that's where all the technical effort went into showing that this part is convex in Y. And once you have that, it becomes kind of easy. You can show by weak majorization that if you have it for alpha, then using this, just applying Karamata's inequality, you get it for beta. So that's kind of the idea for going from alpha to beta. So this was the same idea which we used to show that Hillinger implies the mutual information. Except that we have now worked with this ugly function, show that it has some nice properties, and it's increasing convex and so on. So it was just a bit of work involved. Now, so is there any questions so far about what I'm trying to do? I'm just trying to get a family and then trying to show that if you prove for alpha, there's a nested family. Okay. So the second result is to observe that the Hillinger conjecture can be rewritten as the following. The expected value of this gap is at least as bigger than square root of 1 minus EF squared minus 1 plus root 1 minus rho squared. So we can ask whether we can get some good lower bounds for this function, and if we can get some good lower bounds, then can we prove this?
Hey, Chandra, is this known, actually I guess not. I was going to ask if just in the case where F is unbiased, do you have any further progress on like where expectation of F is 1/2 or 0 or whatever?
I will come back to it later maybe, yeah. But when it's biased, you do have some results, right? So there are some regimes for which we know it's true.
Oh yeah, it's kind of extreme bias, yeah.
But for unbiased, we don't have any results right now, but we'll come back to it later. So because it's kind of so even the lower bound I'm going to show you will prove it for some regimes. So it's a different lower bound. Now the question is turning to how do I get lower bound on this quantity? So it turns out now probably Sergey will recognize this function. It's the thing he wrote in 1996. So we are going to show that this is lower bounded by the Gaussian isometric function times square root 1 minus rho squared. And in some case, some parameters, this is better than this bound. So and I'll come back to it. The last part is saying that maybe we are all looking at it the wrong way, and then maybe we should look at it differently. So the statement here is that if you define, so G is a standard Gaussian density, G hat is the density up to a certain point, and you define psi of A to be twice the density at G hat inverse. And then you get this function. So in the proof of this theorem, I think all the heavy lifting was done by Sergey, and we just showed that we can mimic our problem back to his recursion. Okay. So the one obvious attempt to proving the any lower bound is to use induction. So you take a function f, you define f plus to be the function where the last coordinate is fixed to be plus 1, f minus be the function where the last coordinate is minus 1, then you get two children on small dimensional hypercube. And you can observe that t rho at the parent function is 1 plus, and this is just basic calculus, basic Fourier answers, you can get this. And then the next step is that we apply the joint convexity of this function to lower bound this difference in terms of the child functions. And then you have the gap between. So in some spirit, this is similar to what Genuine Park and Jeff Kahn showed. This is similar to what other people. The idea is similar. You take baby functions and you then bound the parent function by two children function and the gap between the means. And once you do this, you see that you only need to guess a phi such that this inequality holds. Now phi depends on rho also. So if you can find any phi that satisfies this inequality, then you get lower bound. That's how satisfies the base case. This is not yet in the form that Sergey considered, so we make a further guess. Let's assume that phi has a particular form, and that particular form is that we assume that phi of A is square root 1 minus rho squared times psi of A, and then it turns out that the equation to show this is reduced to exactly the form that Sergey considered. So we just need to look at this. So which means it's possible that you might have a better guess for phi here, and you can improve this, but at least this works. And that's exactly how we reduce it to get lower bound. Okay, so that's kind of the idea for reducing it. And so this is where we use Sergey's results, say that you get the function equality was solved, and that's how we get the value of psi of A, and we plug it back in, and we get the result. So these are the kind of two works that I want to mention in the beginning. But then the next work I want to say is kind of this is kind of where this is really work in progress. It means even last week we were working hard on this. So one of the things that we were worried about this previous conjecture is that when it's unbiased, as Tom said, when it's unbiased or when it's biased to a large extreme, it's easy. So we don't think it's the right form of the conjecture. The right form of the conjecture would have the property that if you prove it at rho close to 1, then it should automatically imply for all rho. Because you want to use the semi-group property, you want to say if you just add a bit of noise and you can prove it's behaving properly, then you should be able to just concatenate and get the whole thing done. And that's the kind of conjecture we'll be looking at. So I will use the board at some point to sell some conjectures because it's work in progress. I didn't prepare the slides for that because I don't think I should put it out because it's not published yet. So here is a inequality that really came about when we're looking at relay channels. So this is ongoing work with Amin Gohari and my student ZJ. So it says that you have a binary random variable and x is uniform in the hypercube and y the same setting, then the conjecture states that the binary entropy of this quantity, or this is a typo, it should be IVYN. So, and A star B is the binary convolution. So this is the conjecture that we have, and so first what I want to prove is that if you prove this, that implies the Michelin conjecture. So let me just, sorry, I need to correct this. Let me try to use the board. So the right conjecture is that H2 of 1 minus rho over 2 convolved with H2 inverse of 1 minus IV by n by IVXN is less than or equal to 1 minus IV by n. So now if I put V to be a function of Xn, then you get this. So this quantity is at least as big as H2 of 1 minus rho over 2, or H, because that's convolution always moves it towards center. So then you get I f of Xn Yn is less than or equal to 1 minus H of 1 minus rho. So this is bigger than or equal to, less than or equal to. So clearly this conjecture is stronger than the Michelin conjecture. But the main thing is that this satisfies the semi-group property. That means if you prove this conjecture near rho equal to 1, you're done for every rho. And this is because you have a very nice recursive structure. You can put it in this. Another way of stating it, if you plug it the other way, you can think of it like 1 minus rho over 2. H2 inverse of 1 minus IV Xn is less than or equal to 1 minus IV by H2 inverse of. So you can see similar form coming up, and now you can concatenate, and you can prove that it's enough to look at this conjecture near rho equal 1, or really at derivative at rho equal to 0. And the case for n equal to 1 is another result in theory, which is my primary field of research, and that's called Mrs. Gerber's lemma. So we know the validity of this at n equal to 1. So this is the conjecture we're working on for like last few months, and we actually worked on different conjecture, but this is the one that's, so a natural induction approach seems to work, which means that we could do the same induction approach, and right now, as of last week, it essentially says it's a small dimensional calculus problem, which is now true by simulations. So you don't need to prove, so you have a small dimensional calculus problem that seems to be true by simulation, so which if you can formally prove it, you prove the whole conjecture down. Okay, so, and that comes from induction. So I can talk about this offline to people who are interested, but this is really the way I'm thinking about how to go about this problem. Once you get the right form of the conjecture, it seems to be rather easy.
Sorry for pushing. What is the small dimension?
6. So that's why 6 is not too bad. So okay, I can even tell you. So 6 is at the point where the grid search is just not too good, right? Because you still can't do very fine grid search.
So is it 6 but over the cube, or I mean, what's the space?
0, 1 to the power 6.
0, 1, the continuous interval. Yeah.
But it's just, there's no dimension, there's no end, there's nothing. So it's just.
No, I understand. Yeah.
So, and that will be.
I was just wondering if it was like 0, 1 to the 6, or like positive reals to the 6.
No, 0, 1. It's a compact set. It's a very small. But if you look at so the basic, it really depends on the property of the following function, which is phi p of x. You can define phi p of x to be h inverse h2 of p star h inverse of 1 minus x plus x minus 1. And it's you can define it as terms of a small dimensional variable in terms of Phi of x. And that's kind of, it just comes from induction. But the strange thing here, I'll tell you something about why the calculus part was a bit tricky. So even if you go n equal to 1, if you write the derivative down, we don't have direct proof. But if I write this form down, this just means Gerber's lemma. So we are even missing a calculus analytic way of showing all of these things. So we don't have a good control over this, but we know it's true. Okay, so observe that when rho goes to 1, the mutual mean conjecture reduces to E of SF of x bigger than or equal to 1, and this is known as either a discrete Poincare inequality or Harper's arithmetic inequality. So even if I prove this at rho goes to 1, you get a stronger strengthening version of this as well, because it implies this as well. So there is a bunch of things that we need to prove. So for instance, if I take, so one of the guesses we have here is that, of this function we studied is whether Phi of 1 minus x is completely monotone. So this seems to be some kind of properties we seem to observe, but we don't know, we can't prove yet. We don't need this, but it's just property that we can observe. So that's kind of what I want to say about the conjectures. So if you want to have more details, you can ask me. I'll be happy to go over this. Now, one of the things that, let me go back to, so this is just the dimension form. So I'll address Tom's question. Maybe I'll shut this down. So now I can use the board to say something. So now if you look at the square root function, which is what many people are interested in, then the derivative at 0 will be, you want to show that for every v, you want to show an inequality of this following form. So these are two adjacent points on the hypercube. So this is what I didn't write. So this seems to be inequality that seems to be true, and if you prove this, you essentially show the Hellinger conjecture. Now this would be but however, this doesn't seem to go, induction doesn't seem to work here. So this is kind of a valid inequality, and in particular if you put, the good thing about such an approach is that if you fix the mean, you only need to work with a fixed mean. The problem with the approach, which general induction is that if you fix a mean, the two child functions may have different means. But in this case, you are just doing a differential equation on the thing the same mean, so the mean doesn't change. So, but this is not, okay, this is a hard approach. This is what we tried for many months. We couldn't make much progress on this. Then we went back to information, we could make some progress on this. Okay, so that's what I really wanted to say. As I said, I speak fast, so you can, I finished a bit early, so you can have time for questions.
Did you finish?
Yes.
Yeah.